In today's class, I will discuss viscosity. It is a very important chapter in fluid mechanics. For class 11 physics, I will cover topics: what is viscosity, origin of viscosity, velocity gradient, coefficient of viscosity, and physical significance, streamline and turbulent motion, Reynolds number, Stoke's law, terminal velocity, and Bernoulli's theorem. So let us start. We start viscosity. Here we see a moving water. In a river, the upper layer of this water is moving and subsequent layers also move. At bottom, the velocity of this layer is 0. So we take a segment from this flow. How every layer of this flow reacts to the velocity. For simplicity, we consider three adjacent layers of this flow. The yellow one is in the uppermost, green in the middle, and white is fixed with the bottom. Clearly we are seeing the topmost layer is moving first. And the movement gradually diminishes at bottom as it is fixed. So the velocity of topmost layer is greater than its adjacent layer below it, and subsequently all the layers follow this path. There exists a tangential stress between any two layers of the liquid which are moving relative to each other. How this tangential stress occurs? Fastly moving layer is retarded and accelerates the slowly moving layer. Now we introduce velocity gradient. If we consider two adjacent layers, then there is difference in velocity dv, and the interlayer separation is dx. So dv dx measures how much velocity it increases with distance. So dv is change in velocity between two layers and dx is the separation between the two layers. Now coefficient of viscosity, we write Newton's law of viscous resistance. Small f is proportional to velocity gradient. This small f is the tangential stress. It is measured at force per unit area, and dv dx is the velocity gradient. If we remove proportionality constant, then f equals to eta dv dx. We term eta as the coefficient of viscosity. So few words about viscosity. It is the friction in the fluid, friction between adjacent layers when there is a relative motion. So physical significance of coefficient of viscosity, f equals to eta dv dx. When dv dx equals to 1, we find f equals to eta. So eta is the tangential stress when the liquid is in orderly motion. When the liquid is at rest, we don't observe such phenomena. So for a liquid at rest, the coefficient of viscosity does not have any physical significance. Now we will study streamline and turbulent motion. We consider a pipe and water flows through it. We take three different positions of this pipe, A, B and C. We measure the flow at these three different positions A, B and C as V1, V2 and V3. After some time, we again measure the flow at the same positions A, B, C, and if we find at these positions the velocity is same as before, V1, V2 and V3, then we will call this as a streamline flow. Now, definition of a streamline flow. With the passage of time, the velocity of whatever particle happens to be at A is still v1, and that at V is still v2, and so on. The liquid will be said to have a streamline flow. The path followed by the particles in such a flow is called a streamline. Now, this pipe with a changing aperture. The cross section here is greater and here is lower, and the streamline flow continues. We find the separation between the streamlines here is greater and here is narrower. As the streamlines comes closer together, the pressure increases and the velocity of the flow also increases. Properties of a streamline. No two streamlines can cross each other. If they cross, then at that point, at the crossing point, each particle will have two velocities, which is not possible. The tangent to a line at any point gives the direction of flow of the fluid at that point. Now, when the streamlines crowd together, that means comes closer together, the velocity of the flow increases. So these are the properties of a streamline. Now, when this streamlines breaks, here for the flow through this pipe, at the axis of the pipe, the velocity is maximum v0, and on both sides it gradually diminishes, and at the wall the velocity is 0. Now, there is a certain velocity above which the streamlines becomes turbulent, and there comes critical velocity, and this critical velocity is measured as k eta by rho r. K is the Reynolds number, eta is the coefficient of viscosity of that liquid or fluid, and rho is the density, and r is the radius of the pipe. K is generally 1000 for narrow tubes. It is determined by experiment. Now, Stokes law. Stokes law describes the motion of small spherical particles in a viscous fluid. Here we took a sphere of radius r. Now it states that the frictional force, that is the dragging force experienced by the particle moving through the fluid, is directly proportional to the particle's radius r, the fluid's viscosity eta, and the particle's velocity v. The law can be mathematically expressed as Fd equals to 6 pi eta r v. Now, the ball falls through this fluid due to its weight W equals to mg, and when this ball moves, the adjacent layer of fluid also moves with this ball, but the rest of the fluid is in fixed. So there is a relative velocity between these layers, the adjacent layer with this ball and rest of the part of the fluid. And so there comes Stokes force Fd equals to 6 pi eta rv. This is against the moving body. So this is a frictional force in the fluid. Now we are going to calculate terminal velocity. So terminal velocity achieved by acting three forces: the weight of this ball, the Stokes force, that is the dragging force in upward direction, and the buoyancy of the fluid in upward direction. So these three forces, if r is the radius of this ball and sigma is the density of this fluid and rho is the density of this ball, then weight of this ball is 4/3 pi r cube rho g, and Stokes force Fd equals to 6 pi eta rv, which is the velocity with which the ball is moving, and buoyancy is 4/3 pi r cube sigma g. At equilibrium, weight equals to Stokes force plus buoyancy. Now, the direction of the forces: weight in downward direction and the rest of the two forces in upward direction, that is Stokes force and buoyancy. And we get this equation 4/3 pi r cube rho g equals to 6 pi eta r vt. We call this v as vt. It is termed as terminal velocity plus 4/3 pi r cube sigma g. And we get this expression for vt equals to 2 r square g rho minus sigma by 9 eta. So this terminal velocity depends on the radius of this ball, and with acceleration due to gravity at that place, with the density of this ball and density of the fluid and the coefficient of viscosity of this fluid. Now we study Bernoulli's theorem. Bernoulli's theorem applicable for incompressible fluid, and the fluid will also be non-viscous and it will maintain a streamline flow. Then Bernoulli's equation reads: a fundamental principle in fluid mechanics. It describes the relationship between the pressure, velocity, and elevation of the flowing fluid. It states that the total mechanical energy of the fluid remains constant, which can be expressed mathematically as half v square plus gh plus p by rho equals to constant, where p is the static pressure, rho is the fluid density, v is the fluid velocity, and g is the acceleration due to gravity, which is the height above a reference point. Now, Bernoulli's principle can be derived from the principle of conservation of energy. This states, in a steady flow, the sum of all forms of energy in a fluid is the same at all points that are free of viscous forces. This requires that sum of kinetic energy, potential energy, and internal energy remains constant. There are many applications of Bernoulli's theorem, as we should not stand near a moving train, or why the roofs wipe out in a cyclone. All are examples of Bernoulli's theorem, where velocity increases and thereby reducing pressure. Now, venturimeter. This part I will discuss in my next talk. So, thank you for today.